Riley has provided energy modeling consulting services on a wide variety of building types for various purposes. Riley is an executive member with the IBPSA BC and a BC chapter of International Building Performances Simulators Association, and has been involved with the development of STEP code and the City of Vancouver energy modeling guidelines. Please welcome Riley.
Hello, everyone. Looks like a pretty light crowd in here, so I think we're going to have to keep it pretty informal. If you guys have any questions, please feel free to ask during the presentation. I think we can accommodate that. So with that said, let's get to it. This is the last thing of the day, so I'm sure you guys are eager to get done. So I guess I'll just start with who here has, well, maybe not last summer, because last summer was pretty cool, but the summer before, who here had a bit of issue with wildfire smoke? I mean, it was pretty common all around the province, not just down here, but of course further up north, Burns Lake, whatnot. I actually spent 6 years fighting forest fires while going to school, so definitely breathe a lot of smoke like that myself, and it does seem like it's becoming more of an issue. And who here has been in a house in the summer when you're having a hard time sleeping on a hot summer night? Right? That's pretty common as well. So this presentation is going to touch on both of those items and how those may be applied in building design and how you can design to sort of mitigate those. So, I mean, this is generally a presentation to outline some of the work we did for BC Housing on developing a design guideline for mitigating overheating and indoor air quality issues. We worked with Integral Group and Hughes Kahn and Marler Architects on that project, and so just want to make sure they get some credit here too. So the main agenda we have here today, we're going to go over some learning objectives, identify the things we'd like you to leave here with. Some background information about what we're talking about. We're going to talk a little bit about resilience in building design and what does that actually mean. We're going to talk specifically about overheating. That's probably the bulk of the presentation. We're going to talk about indoor air quality as well. We're going to talk a little bit about balancing these targets. We sometimes have multiple requirements of a building, and sometimes designing for one can affect how the other performs, and there may be some balance there. We have some key design strategies to address both of these items, overheating and indoor air quality. And then we're going to end up with some, actually I do have a couple examples at the end that I'll try to squeeze in from real projects, and then some discussion. So the things we'd like you to leave here with today is understanding how the STEP code looks at overheating. It's not, overheating is kind of a subjective thing. To say if one is too hot, it's kind of personal. So we're going to talk about how that's dealt with in this STEP code specifically versus some other metrics for that. We're going to look how this is now different from the previous code where it may not have been addressed before or addressed differently, and describe how this might show up in building permit submission. So of course, you guys as building officials, you're not doing the design of the buildings, but there are now requirements that are related to these items. And so having some background knowledge and some of the design strategies and the metrics will probably be very useful for you guys in reviewing submissions. And of course, we're going to talk about how is the climate changing and how are the codes changing and sort of the future involvement of this area of research and of design, particularly as we adopt higher STEP code values and the climate changes. So again, this is the actual supplement itself. It's freely available on BC Housing's website. It's a really nicely put together document. Hughes Kahn and Marler Architects has an illustrator on staff who does fantastic work, so really helps put the information in a nice, clear to read graphics, nice layout, easy to understand and follow. It's really nice work.
That's the guideline that is a directive for BC Housing. It's all social housing.
No, not necessarily. So BC Housing does have a design standards and construction guidelines, and that is the document that specifies what their requirements are. This is a supplemental guideline. So this will speak to identifying a little bit more on what are the issues that we're trying to address and some strategies to how to achieve those. They aren't necessarily laying out requirements themselves within the document. And Wilma from BC Housing here, please correct me if I'm wrong. Yeah.
Yes. So if you go to BC Housing Research Center, just type in energy step code and this will show up.
So let's start with a little bit of background as to why we even built this resource. So the climate is changing. We know that. I hope we all agree on that. The climate is definitely changing, but how is it changing, and how much, and how will that affect how buildings are designed? We have an overall temperature increase projected between 1.3 and 2.7 by 2050. The range there we'll talk about a little bit in the future, later on the presentation. There may be heavier rains, longer dry spells. Certainly, I feel like I've experienced that. I live in Victoria, and in the last few years there have been some moderate drought conditions, even on Vancouver Island, which you'd think would be full of rain, but not necessarily. More heat waves, and I think that's particularly of interest for the design for overheating, because even if your overall climate is fairly cool, if you do have that one extreme heat wave, that could be a problem. And so we need to be aware of that. More severe wildfire events, definitely happening. I think we're all pretty aware of that with the smoke in the last couple of years. And of course, we have evidence that the temperature has already been changing over the last 100 years. So what does this do for buildings? How does this relate to how we design buildings and how we occupy buildings? Well, there are certainly some occupant health and safety concerns. You have issues with potential overheating for, you could even have people, death, right? If you have someone that's completely overheated and unable to open their window or get help if they have perhaps compromised health already. You have impacts on energy consumption. As the climate changes, you maybe have some more cooling energy or fans or et cetera, or maybe less heating. That's another thing to think about too. You have some financial risks to building owners. That's particularly, I think, related to costs of upgrades later. Like maybe a building wasn't able to provide adequate air quality or comfort. They may need to retrofit that building later to provide cooling. That would be an additional cost, not to mention other issues regarding to more of the extreme events like heavy rains, et cetera, that might actually damage buildings. So we know these things. We know that the climate is changing, that these are potential risks. We've been doing some work. A lot of other people have been doing work as well. UBC is about to publish a study related to overheating specifically. That'll be available, freely available. So now we're trying to identify how do we plan for this in the future, and how do we incorporate this into our building design? Or you as a municipality, what sort of things do you think you want to ask people to consider, to at least consider? Maybe they don't need to meet certain requirements, but at least if we start the conversation, I think that's a good first step. So in developing this guideline, there was a lot of discussion around resilience in building design. And I didn't exactly know what that means, and I still think it's a little bit of a nebulous term. Resilience in what way? I think a building could be resilient to either extreme weather events. It could be resilient in terms of structure. It could be resilient to fire. But of course, then you're looking at resilience in terms of its ability to house its occupants in a safe way. So you may be looking at having ways to mitigate smoke events getting into the building, mitigating overheating. And one of the issues that gets talked about is using every building should have, or with a multi-use residential building, for example, if it did not have cooling, then there should be some portion of the building that can act as a refuge during a heat wave event. So those are the types of things that come up when we talk about resiliency in building design. So again, the two main topics are summarized in this very dire-looking diagram here. We've got the sun setting on a forest fire. So overheating, of course, this is a major concern, and indoor air quality issues. And this is primarily, we're talking about outdoor air pollutants, but there are indoor pollutants as well that we touch on as well. So we'll start with overheating. So what is overheating? I mean, I think everyone, you say overheating, they understand, yes, too hot. Okay, well, Too hot, how hot is too hot? That sort of thing. And how does this happen? So we're thinking about this through the lens of not only the current climate and building design, but in terms of future climate and with the changing building standards and how those two intersect and maybe create an additional risk for overheating. So like in this diagram, we're looking at, an increased performance of the envelope. Maybe it traps more heat in the building and the climate's getting warmer. So these two things create a potential risk for additional overheating in buildings that we're designing and building today in the future. So just to break this down a little bit further, we have a diagram with all sorts of different things that can contribute to overheating. Generally, we have internal gains. So these are all the things that are generating heat inside your space. You have cooking, you have your microwave, you have your fridge, your water cooler, computer. Those are all plug load internal gains. Those aren't things that we can necessarily control. Those are things that people will have in their buildings, and that's just the way of it. I mean, you can't really cook, especially with an electric stove, with any less energy than it takes already. You have people. People are going to still be putting out approximately 90 watts of sensible heat each, particularly if you're doing push-ups like that fella. And then, of course, you have solar gains coming in through the windows. So a solar gain through the window is something that we can control in design relative to internal gains, which we may have less control over, if any at all. One that's actually not shown here is lighting. Lighting is another gain that is one that we can control to some degree. Then, of course, you have some other factors to consider. So from the bottom right there with that little sort of map marker, so that's just kind of indicating some sort of a reason or hazard that you wouldn't open up your window. So the person upstairs, they have their window open to keep them a little bit cooler, but the person downstairs, they don't have it open. And that could be for a variety of reasons. It could be for children not falling out of windows. It could be for security reasons, to not have people potentially accessing their suite. And it could be for noise, or it could be for outdoor air pollutants. So there's a variety of issues, or reasons rather, why someone may not want to or be able to open up their window. Another one not really shown there as well is, what if the person is unable to, for mobility issues or mental health or physical health, they're not able to recognize that they need to open the window or physically go and do that. So it's a bit of a complex puzzle with all these different inputs to consider. Yeah, sure.
So you showed the envelope or the insulation in, I think, fifth.
Yep, number 5 up in there.
How does that contribute?
That's a good question. So if you talk to some people, myself maybe included, I might argue that adding more insulation to a building may not necessarily increase the risk for overheating. If you talk to people that design passive houses, they would say that no, there's no more additional risk for overheating in a building like that. That's not necessarily the case, and I've actually played around with some simulations myself just to evaluate this. But the general concept is that there is a risk that with a more insulated building, you will retain more heat, and then you can have more of a risk for overheating. But what it really comes down to is, are you able to get rid of that heat at night? So if you have a building that you're not able to cool down at night, then that will start the next day warmer, especially if it was more insulated, and then you'll be sort of at a deficit. You'll be starting at a warmer temperature and you'll overshoot higher. So it's not always a risk, an additional risk, but it is something to consider and to understand.
If you have passive house all designed properly ventilated and you air pipes and you don't have interaction with outside air, which is more harder in summer. So in a way, I don't know how it relates with the insulation, because passive house will have that kind of insulation, probably not the regular ones where the core isn't even required that much insulation. But in a way, what is the scenario here? If that is not passive house, but it just design over insulation more than what is required, then probably this adds to the overheating aspect?
It has a potential to, yeah. I think that's the main message, is that it's one of the factors that's included. It will affect how much heat is left in the building or is conducting in from outside. That's another thing. It could help in that case. Like if you have a lot of thermal mass in your building and you're able to keep it cool by night ventilating it, right? Letting it cool down to the same outdoor air temperature at nighttime. And in the daytime, if you're able to close your windows and keep it tight, then it'll be kind of like a cooler, right? So it could be a benefit. It's not as simple as saying it's always bad or it's always good.
So, you know, you just have a calm side effect when you are doing morning.
Exactly. That's exactly it. And then understanding, you know, some of the risks that may be associated with that, particularly as the energy performance standards are ramped up over the coming years, and how that changes, you know, how this works. You're welcome. So thermal comfort is, I think, quite an interesting topic. There's a lot of science involved in it about how because ultimately it's a perception. It's a perception thing. Like, why do I feel warm or cool maybe when someone else doesn't? It has to do with your age, your metabolic rate. Some people run a little hotter than others. It has to do with your behavior, right? So your level of activity. And then, of course, how much clothing you're wearing, right? Like some people would be wearing different levels of clothing for a variety of reasons. This all affects heat transfer and what we perceive as our own thermal comfort. Some of the physical considerations are, of course, I mean, we typically talk about air temperature, but air temperature is actually less important for your perception of thermal comfort than radiant temperature, so the temperature of the surfaces around you. The reason we can use air temperature alone as a metric is because most places like this room here, the surfaces are all going to be more or less the exact same temperature as the air. If you're next to a window, however, you may, in the wintertime, that window will be cooler and you'll feel colder. In the summertime, conversely, it'll get hot in the sunshine. So there's a lot more to it than just air temperature, which is good to know, although using air temperature as a proxy for total thermal comfort is acceptable in most cases. The truth of it is that it becomes very complicated to try to delve into all these factors. So as a result, the STEP code has introduced some overheating limits. So these overheating limits are sort of a modified thermal comfort metric that's based on ASHRAE 55, which is a standard for thermal comfort of occupants in buildings, but it is not equal to it. So that's an important distinction. Sometimes we have that confused. We've seen some clients saying, oh, we need it to be compliant with ASHRAE 55. Well, if it's a STEP code project, no, that is not the requirement, and it's good to understand the differences between them. The BC Energy STEP code has a limit of 200 hours, and again, this is summarized in the City of Vancouver modeling guidelines. That is the upper limit. You're never allowed to have more than that. We'll talk about what these hours are. There is also some language in there for 20 hours of overheating for vulnerable occupants. So again, this is for maybe it's a assisted living facility or something like that. You maybe want to have a bit more comfortable. Some people may be more at risk. These limits are generally based on an 80% acceptability in ASHRAE 55, which means that 80% of people will say that's more or less okay, but that's not everybody. So the way that these are actually determined in practice is that there's a calculation that looks at the average air temperature in a month. And based on that, and this calculation from ASHRAE 55, you come up with a maximum temperature for that month. And the idea here is that this changes throughout the year because humans are pretty good at adapting. There's a lot of research that shows that adaptive comfort models are very useful, they're accurate. So we're more accepting of a higher temperature later in the summer because we're more used to it. Similarly, if you lived in a hot climate, you would be more accepting of a higher temperature. So the other thing to point out here is that the City of Vancouver modeling guidelines that talk about overheating limits, they list values. They list for a month, this is what your limit is. If you're not in Vancouver, those are not the right numbers. So you need to calculate, your modeler needs to calculate those from the climate file that they're using. And that's an important thing, I think, for building officials to know, so that in your reports that you're getting from your modeling team, if they're listing overheating hours, it should also state where those overheating limits came from, and just to double check that they do align with the climate file. It's based on the actual climate file. So the process would be, here's your project. It is in, I don't know, Grand Forks. So you go to Grand Forks, you look on a map. There's a lovely website called EPW Map, and it has weather files shown on a map. And so you find the nearest CWEC 2016 weather file. That's the type of weather file that we're mandated to use for step code modeling. And you use that file for modeling for that location. It's not necessarily one climate zone per climate file. In fact, you have a huge variety of climate files for one climate zone. So another note about this is that any hour that is a room is over top of or above the limit is counted as one overheating hour. It has no consideration of how far over. There are no maximum temperatures given. So even if you're saying that your overheating limits are met, you still may have some peak temperatures for a few hours or a day that could be problematic. So that's something else that could be considered if you have a location that has big spikes. What we find is that projects that are in the Lower Mainland or on Vancouver Island that are near the coast, they're heavily dampened by the ballast of the Pacific Ocean. And so you don't get very high peaks in the days. Whereas you go inland a little bit, so up to even just Abbotsford. And in those areas, if you look at the overall heating degree days, the climate looks fairly similar, but the daily peaks, because you don't have that ocean there to keep it cool, the daily peaks spike up quite a bit more. And so you have significantly more overheating issues in there. So here's what that might look like. So this would be us pulling data out of our model. This one looks like it was either very well shaded or in a very temperate climate. So you have the limits at the top there. These are kind of typical limits for, I think these ones are maybe for somewhere on southern Vancouver Island, maybe Victoria or Souk or something. So the limits are, reasonable, 25 something. I think in Vancouver they get up above 26. And so you're looking at, for each month, for each space, how many hours is that room above the overheating limit? What is the total annual hours? And then for the report for the entire building, we report the single worst space. So what we end up doing in our analysis and modeling is we do the overheating analysis, we figure out which is our worst case scenario, and then we can look at strategies to mitigate overheating in just that space and any others that might require it. Okay, so a lot of this work has been talking about future climate modeling because, again, we're using data that's from the past 30 years for our current climate files, but we know that the climate is changing. So there are generally 3 different scenarios that we look at. These are the RCP scenarios, 8.5, 4.5, and 2.6. They're essentially the 2.6 is best case, if we really get our stuff together and make changes to how our carbon emissions. The middle case is kind of a business as usual, more or less, or maybe with some reductions. I'm not entirely sure, I can't recall. And then the 8.5 is our sort of worst case scenario. So, of course, there are so many different scenarios. We can't predict the future, but generally these are the 3 scenarios that will be talked about in modeling future files. So where do you get these files? Well, you can get them from the Pacific Climate Impacts Consortium. That's an organization based out of UVic. They've created algorithms to morph climate files from locations into future climate files of all of those different scenarios, and for different time periods, for 2030s, 2050s, 2080s. So there's a lot of good data out there, and there's more coming. ClimateData.ca and WeatherShift are also good sources for that. This is becoming something that we're seeing quite a bit of interest in. it's almost something that we're providing as like a standard analysis, just even if it's not being asked for, we think it's almost best practice to say, okay, well, in order to model for step code, we're mandated to use these modeling guidelines, which include this specified weather file. But we know that that weather file that we're using is based on the previous 30 years, so it's already out of date. So we can also run a couple scenarios with these climate files because it's fairly easy to do, and just give some sense to say, okay, just so you know, here's how things might change in the future for your consideration. And we can look further into it once we've done that. Okay, now on to indoor air quality. So indoor air quality I think it's pretty straightforward. It's very important, right? I mean, we need good air quality because we breathe all the time, and we can't, if we're in a contaminated environment, that would have some direct health implications. And so it's very important that we have good air quality. Based on our lovely list here, it's been linked to pretty much everything bad that can happen to you. So got to make sure your air is good quality. In terms of code requirements, I'm not aware of any specific requirements for indoor air quality in terms of like what the contents of the air, like parts per million of this or VOC content. I mean, of course, there are some other standards that talk about, like LEED, for instance, talks about indoor air quality testing for volatile organic chemicals from interior finishings, et cetera, off-gassing. But other than that, generally, we're talking about just providing a minimum fresh air supply to a space based on ASHRAE 62.1 or the Part 9 requirements for residential suites and single-family homes. So there are some standards out there, but not necessarily for like indoor air quality testing of the contents of the air. So what are the things that we need to think about with indoor air quality? We have a variety. Generally, we have indoor pollutant sources and we have external pollutant sources. Indoors, we have cooking, cleaning products. That can be a bad one. Material off-gassing. I think generally industries are producing more and more products that are aware of these things. They've been sort of highlighted through programs like LEED. External things, traffic. Traffic could definitely be an issue. Big trucks going by, blowing black smoke from the diesel. Industry, like I was just out mountain biking near Duncan, and of course the pulp mills there, it's pretty evident with the smell that they give off that there's something in the air. Construction, you have some dust issues from construction. They get tracked around by trucks and blown around in the summertime, so that's another contamination source. Hazmat emergencies, that could definitely be an issue. I actually, a long time ago, I worked for Kinder Morgan Pipelines, if you'd believe it, long before they became so controversial. And I was involved with the hazmat emergency there where there was a pipeline burst in Burnaby, and it's definitely something that could happen. And noise. Noise is certainly one, particularly here. I mean, just think we're just across from the airport, and there's definitely some noise issues in terms of, I wouldn't call it an indoor air quality issue, but we've included it in here because otherwise it would be all by itself. And of course, wildfire. Wildfire is something that is becoming more and more common in terms of an issue. I had a friend of mine, his mother was very sensitive to it the other summer, and it was a problem. It was a real problem. We needed to find some ways to help her, filter air for her place and get an air purifier. And it didn't affect me so much, but her being older, it was definitely an issue. So like I was talking about earlier on, we have a variety of targets that we're designing towards. And sometimes designing for one may affect another. And in fact, that's always the case. It's just a matter of how much. So in the step code, we have, for Part 3 buildings, generally, we're looking at total energy use intensity, right? So all the energy use of the building per unit floor area annually. The other one is the thermal energy demand intensity. So this is a metric that's looking at just the heating load of the building, regardless of how that heating load is met. So that would be your total heating load divided by your floor area. Overheating, of course, as we just talked about, that is a requirement. And then air tightness. So a variety of different factors that we're trying to meet, and sometimes they intersect opposite. You increase one and you drop the other one, that sort of thing. Okay, it's quiz time. So I hope this works here. So here's our building, right? We have a variety of strategies we're going to apply to this. So we're going to go through and figure out how are each of these measures going to affect those targets. So we'll just go, how about exterior shading? So how is overheating and the TEDI affected with exterior shading? So if you add exterior shades to your building, TEDI, which would just go up or down, and overheating up or down? Anyone? Overheating goes down, yep. And what about the TEDI? Goes up? Good, I heard an up back there. Good one. You're right. Now, there's a small caveat to that, in that it may, if it's really, really well-designed shading, then maybe it wouldn't make your TEDI go up, or at least not very much. That's a good question. So adding shading to your building is great for keeping the sun out, but sometimes you want that sun. In the wintertime, that's passive solar heating. So in some cases, if you're not careful about how you design your shading, you can actually increase the heating load of your building. So again, this is this trade-off with, we're gonna be cooler in the summer, but we're gonna not get as much heat in the wintertime. So when I say you can be clever about it, let's say this building, well it is, it's facing, or I think it is, to the right is south, let's say. A beautiful thing about a south-facing building is that you can put a horizontal shade on your building, and then in the summer, the sun is at a very high angle, and your building is well shaded. And then in the shoulder season and in the winter, the sun is lower, and now the shade is no longer shading your window. So it's perfect. It's passive. It sits there. It doesn't do anything. Doesn't need any maintenance, and it just works. You get sun when you want it, and not when you don't want it. But inevitably, you're going to have some change in your heating. You could do the same thing with a deciduous tree for a low building, like low floors. The tree has leaves in the summer where it shades when you want it to, and then leaves fall off in the winter when you want the heat. It's a pretty beautiful solution. I've even seen there's a building at UBC, SIRS, that has some trellis on the outside, and they have vines that grow up. So in the summertime it's shaded, and then they die off in the winter, and it lets a little bit of light through. A little bit of shading still, but. Okay, next one. Operable windows. Oh, sorry, I didn't ask. Gave it away, freebie. So operable windows, you have a lower risk of overheating, but you may have a higher risk of indoor air quality issues, particularly if you're beside some busy trucking traffic or something like that. So again, this is a trade-off. Okay, mechanical cooling, low solar heat gain. So that's what SHGC stands for, how much solar heat the windows let in. So if you put a lower solar heat gain window on your building, how is that going to affect your overheating and your TEDI? Okay, Harshan says same as 1. Correct. Yep, it's pretty much the same thing. If you're reducing the amount of solar gains into your building, which is going to help it not overheat as much, but also going to not help it get passively heated. I would probably say that the exterior shading, if we were to make these arrows different lengths, the external shading would be overall better performance than the low solar heat gain, because it would block all the sun in the summertime and let most of the heat in the wintertime. Whereas the low solar heat gain coefficient kind of blocks it all the time, which is not ideal. All right, for mechanical cooling, so let's say you decided to just, you know what, we don't think passive strategies are gonna work for this project for whatever reason, so we're gonna put in mechanical cooling. So how does that affect your TUI, so that's your total energy use, your overheating, and your indoor air quality? Yeah, so your indoor air quality, we're looking at the risk of the indoor air quality, which went down, so the quality is better, so it's kind of but yeah, you got it. So lower risk of overheating, of course, because we have cooling, but it's going to cost us some energy. Then, of course, we have we don't need to open up the windows anymore And so we can have ventilation that can be filtered and controlled. And so we'll have better air quality there. Okay, so strategies to mitigate overheating. So we have a variety of different strategies that we can use. We have passive cooling, we have partial mechanical cooling, full mechanical cooling, and then we can talk about some emerging strategies or some that are just maybe a little less common, but could be useful. So for passive cooling, one of the main drivers for this is your building shape and massing. Of course, the orientation of your building has a huge impact on how much solar gains you have to your building, which is one of the main contributors to overheating, if not the main one. The other thing this affects is how much availability or effectiveness you get from natural ventilation. If you have a typical condo building in the North American market where it's a corridor in the middle and then suites on either side, they call it the double loaded corridor. For every suite you have, you only have single-sided natural ventilation. So if you open up your window, it's not going to be the most effective at cooling off your suite versus if you have more like almost like a motel-style building where you have entrances and like an opening. You have exposure. You have an exterior corridor to access your building, and then your suite is exposed on both sides. Then you can open up windows on both sides. You can have airflow right through with the prevailing wind, and it's much more effective. Building orientation, again, very important. It's not super obvious in this one, but we're looking at the long axis of the building. So in the top left, the long axis of the building is north-south. This is kind of your worst case scenario. You don't really want to ever see this because that long west face is going to get a lot of sun in the evenings. And that low solar angle sun is kind of hard to deal with. You can't just put a shade, an overhang on it because you end up with this sun that gets nice and low in the sky. So therefore you need to block it vertically, but then you're blocking views and it's a little bit more tricky. So then alternatively on the top right, you can have your long axis going east-west. This is nice because then you can use those lovely overhangs we talked about. Simple, effective, done. And hopefully you put your emergency stairwells, etc., on the ends of the buildings, and you don't put many windows on there on the short ends, and then you don't have to worry about those so much. But of course, you don't have to have it totally east-west. You can have it a little bit off, like the bottom two, and that's still pretty good.
Which is the worst orientation? Is it west-facing the worst or south-facing the worst?
West-facing is generally the worst because even if you don't have shading on your building on the south side, the sun is pretty high in the sky in the summertime. And so you'll have your building facade like this and your sun's coming down like this. And, a lot of it will be reflecting off of the glass rather than penetrating. Where in a west-facing building, around the heat of the day, 1 o'clock, 2 o'clock, that sun in, late June, early July, it's already pretty far around. And you're getting the very direct, very normal solar gains, and it's very intense and can be really bad. But south is bad too if you don't have any shading. It's just west is worse. Southwest is probably the worst if you really want to get to it. So another way to passively cool your building is using thermal mass. I mean, this isn't necessarily cooling your building. It's more of a deferral of heat transfer. So the whole idea here is that you have a high mass in your building, like let's say you had a nice thick concrete floor or something, or stone or who knows what. So in the daytime, that stone will soak up any heat in your building. It's like a big battery. So as you get sun shining through and it's right on the floor, well, it'll just warm the stone up, which has a lot of mass to it, and it'll take a lot of energy before it starts to actually increase in temperature. Then at night, that you have your windows open and you allow the surfaces to cool off, allow the mass just to cool off and discharge that battery so that it's recharged and ready to absorb the heat for the next day. Very effective, very old technology, very, very good. But of course, you don't always want to build with concrete. Concrete has huge embodied carbon emissions, for example. it's not necessarily always the right choice for the job. So I wouldn't necessarily say that people are going to choose to build with high thermal mass just for passively cooling, but it is something that could be included, particularly if you're already building with concrete. Sort of make sure that concrete is exposed so that you can actually have that heat transfer between the space and the mass of the building. I should point out here that mass timber, which is being talked about a lot more, mass timber can perform reasonably well as well. So in terms of passively cooling the building, what you don't want to do is this. You see a lot of these around Vancouver, and I'm sure they're not very comfortable in the summertime. So you have lots of windows. That's a real problem to overcome. So if it is important for the project to do that, just understanding that, well, you're probably going to have to do quite a bit to address that, to overcompensate. Cool roofs. This is a good strategy as well, particularly for the upper floors. So you can have situations where a dark tar roof can get very, very hot in the summertime with that sun, especially in the summertime when the sun is very high in the sky and it's coming straight down, and then that can radiate through the ceiling. Even if it's well insulated, it can get through, and you'll end up with some overheating issues because of that. Shading, we've already talked about it a little bit, but this highlights some of the different strategies. So strategies really depend on your orientation in terms of what sort of angle of sun you need to block. So this is, I think you guys, hope you can see it well enough here. So you have some external roller shades up on the top right. So that's like at the Olympic Village, for example. Those can be pretty effective. There's some maintenance concerns about those, or at least considerations. Nice thing about those is that you can have shading when you want and then retract them when you don't want it. So it can be pretty good. The horizontal overhangs, which again are great on the south facade. You can see there's a tiny little north arrow at the bottom of the slide. So those are on the south side of the building, which are good. The whole roller shades are on the east side of the building. So again, they have the morning sun. And then we have some perforated metal screens or vertical shades on the west. So that's another way you can deal with solar gains for the west side, is that instead of putting something directly in front, like a roller shade, you can have a fin so that at least for the start of that afternoon, you're shading it, and then maybe you can accommodate just some direct sunlight in the evening when the sun is lower and it's not as intense. Vegetation, I guess I already talked about this one. I jumped the gun on that. So you can see here how so this actually shows not just how vegetation can provide shading in the summer and then allow passive solar heating in the winter, but it also shows, if you look at the shade, the overhang, it's doing the same thing. So it's shading in the summer with the angle, and then in the winter, when the sun is lower, you're getting that passive solar heat when you want it. Another key thing for all buildings that are being designed is, regardless of your shading strategy, is the solar control of the glazing. So there are a variety of coatings that you can use on glass. It's becoming very standard these days to have some, it's not necessarily a dark tint that some people might think associate with low solar gain glass. The coatings are selective so that they block the infrared spectrum, which our eyes can't see. So to us, it looks clear still, maybe has a slight color to it, but generally it's going to be blocking. Like if you looked at it with a thermal camera, it would look pretty dark, but not to our eyes. So that's pretty standard these days. Electrochromic glazing is something that's coming in. It's a really interesting technology. So this is essentially, it's kind of futuristic, but it's actually not crazy. It does have some costs associated with it, but so do a lot of these strategies. This electrochromic glazing allows you to use a controller, and you can actually dynamically tint the glass. So you can change the tint of the glass and how much solar heat gain goes through it with a controller. And that controller can be set to respond to all sorts of different factors. One of the nice things about that for some applications is that it can also be pretty good for glare control. So if you have an office or something and you do want the heat, but you don't want the light for other reasons, and you can tint it. Yeah. It's a good question. I don't know. I'm sure that if you talk to their sales reps, they'd probably say it lasts forever. But I know that it's been around for a while, so they probably do have some good data on sort of the reliability and long-term performance of it. But to me, it seems like it's the cost premium to do it is fairly high, and it's generally more applicable for a cooling-dominated climate like California, where applying a technology like that would actually save you a lot in cooling costs. So it would sort of make sense financially. Whereas here, you could do it, and sure, it's going to help you be slightly more comfortable, but it's maybe not consistent with the cost. So just a bit of a summary of some of the different strategies. 2 thumbs up, extra good, 1 thumb up, pretty good, otherwise neutral. I think we kind of talked about most of them. Window coatings, solar heat gain, vegetation, etc. This is the sort of data or helpful information that's available in the guide. Some nice graphics and sort of basic this is pretty good, this is better, this is best, that type of thing. So cooling by natural ventilation and using operable windows. I say operable windows because generally that's what we see it applied for. So if we're going to be looking at residential buildings, typically Part 3 residential buildings, where we're looking to use operable windows to maintain some comfort in the suite. But this could be for larger commercial buildings where you have an engineered natural ventilation system, where you have openings at the exterior of offices, and you have that air actually come through the building and up to a central atrium where it relieves at the top of the building. We've worked on several buildings that use that strategy, and it can be quite effective for commercial buildings as well. So if you're designing for that, whether it's just simply saying, hey, sure, we want to have operable windows on our building. Well, how much room do we need? What's the area that we need in order to cool it? That's something that your modeling team can help you figure out. The location of it, that's definitely important. You need to look at, like fall hazards. A lot of the windows have limiters on them, of course, so that you can't just open up the whole window and then have something fall out the window, or a person or a child. So there's a lot of things to consider. Again, we talked earlier about security risks, other particular reasons that you may not want to have your window open. Noise is one of them for sure. Okay, so here we have a little example. So we did a 6-story senior housing in Vancouver Island. So it's climate zone 4. It's quite mild. So in the initial design, which was sort of our first cut, we didn't have any operable windows, no shades, basically no strategies whatsoever. We were at almost 2,800 overheating hours. So completely unacceptable health hazard. That's not going to be good. What's that? Well, it did have operable windows, but just sort of for illustration purposes, we ran it with the windows not allowed to open. Yeah, that would be a. I don't think I've ever seen a multi-unit residential building without operable windows. My office has a window in it, but it's not operable, and it's funny, like the mental, like the psychological effect of not being able to open it. Yeah, I feel trapped. So anyways, it's just to illustrate how important some of these strategies are. We start with 2,800, and this is in a very mild climate. We added some shading. We got it down substantially, but it's still completely out to lunch. I mean, we're talking about 200-hour limit here at the most. But this is seniors housing, so maybe even should be lower. And then we added operable windows, and of course, we're achieving some good numbers, or much better anyways. So just a brief little example there of how sort of the magnitude of the effects of some of these things.
This unit probably had an HRV installed for air movement and fresh air and a bit of ambient heating. Is there any way the HRV can be used to cool as well?
That's a great question. We're actually going to get to that later. The answer is yes, but limited amount of cooling. There you go, hybrid or partial cooling. So one of the things to consider for, particularly for residential buildings, but also for commercial buildings, with the step code, we have some pretty aggressive limitations on heating targets. So the ventilation has to have heat recovery on it. When you do that, you do run into some situations where it may be warmer inside than outside, and you're actually recovering that heat from outside and warming up the outside air coming in. Even if it's not by a lot, it's not helping. So one thing to do is to have an HRV with a bypass so that the ventilation coming in doesn't actually go through the recovery and pick up the heat from the exhaust. It just comes straight in from outside. So this is the example you talked about, tempering supply air. So essentially, if you have ventilation provided to your suites, usually we're just tempering it for heating. But if we do have a central ventilation system, we can put a cooling coil in that and provide air that's a little bit cooler, and that can help take the edge off and improve comfort. So then, after you've done some sort of partial mechanical cooling, you can just go full mechanical cooling, which honestly is not a bad option these days. I mean, if you consider how buildings today are marginal in terms of comfort, and then looking at some of the climate projections and the expected lifetimes of the buildings, it seems to me that it's prudent to at least allow for the expansion, addition of cooling later. So heat pumps, very useful. You can have an air source heat pump that's providing cooling to your building. You can have a ground source heat pump. Doesn't really matter. It's just different technologies to move the heat from inside to outside, whether you're rejecting it into the ground or into the atmosphere, either one. VRF systems are becoming more common here, very common in Asia. And so these are essentially using compressors on the roof, and they move refrigerant through pipes down to the suites. The nice thing about these is that they can do simultaneous heating and cooling, and they actually exchange that heat. So if you're in a shoulder season, let's say you have a suite on the west side in September, and it needs a little bit of cooling, but then it's still not that warm out, and the guy on the east side is pretty cold, there's some heat recovery. So in terms of total energy efficiency, VRF systems are really excellent. And it's the sort of thing like if you're going to add in cooling anyways, maybe if you add in a VRF system, then this can provide your heating at an efficient rate for using the same piece of equipment. So rather than adding an additional piece of equipment, you just add in something that can do both. Exactly, yeah. You have one compressor that serves multiple zones, and all of the zones can be in different things, heating or cooling. Yeah, it's pretty cool. Variable refrigerant flow. It's not very descriptive. But so these would look like, there's a variety of ways that they can be interfaced at the actual zone level. You can have like a ceiling cassette, which just looks like a diffuser. I'm sure you guys have probably seen them, even if you didn't necessarily recognize what they were. They're definitely around. Or there are things like a wall-mounted cassette, like you see in maybe a hotel room up high, that sometimes look like a mini split. They can do heating or cooling. It is a heat pump. Yeah, it's just a heat pump. It's just a fancy heat pump. It can do heat recovery from refrigerant to refrigerant. And the different manufacturers have different ways of doing it. So it's kind of proprietary. A little bit people have been a little bit scared of them because of that, thinking they'll be locked in with this one manufacturer for the lifetime of the equipment. But they're widely used, so becoming more and more common. So some other strategies. It's called emerging areas here, but not necessarily emerging, maybe just less commonly used or less obvious. Night cooling, we talked about that before. Particularly effective if you have thermal mass. This could even be done in a commercial building with mechanically operating openings that are opened based on indoor and outdoor air temperature to cool down the mass of the building. And then, of course, that would just take the edge off, and it would keep it cool throughout the start of the next day, and then just give you a little bit of a head start. So this goes back to the overheating risk with additional insulation that you talked about. If you weren't able to do a night cooling, then you would end up losing less of that heat through your envelope overnight. So your building heated up through the day, And unless you're able to open up your windows, it's going to start warmer the next morning than it would have had less insulation. So that's where that can be an issue. And then, of course, capacity for future cooling, which is not really doing anything now, but it's at least recognizing that there could be the need for cooling in the future. And so, like, if let's say I'm as a building owner and I didn't have the money now to install cooling and have it sit there and be used only a bit, and then it wears out in 20 years, 10 years probably, maybe it would be best just to put in allowances for it in terms of power supplies and conduits and ducting. And then down the road, if it turns out that you need it, then it would be much less expensive to put that in then.
The HRV with the bypass option,
Mm-hmm.
can that be a retrofit in existing HRV?
No, the HRVs either will come with a bypass or not. They wouldn't have the room for the bypass. It would requires additional size in the cabinet to actually have a route for the air to go around the core and the controls to do it. So it wouldn't be something you could add on. There might be a sneaky way to do it though.
If you have heat pumps which are kind of efficient during winter and summer, like kind of cooling in summer and then heating in winter, do you still use HRV?
Yes. Yeah. Yeah. So the HRV you would need it for other reasons. So whether or not regardless of all of these strategies, these are all in the context of step code. Step code targets have a real emphasis on minimizing heating load. And one of your biggest heating loads is ventilation. And so it's very critical that buildings have heat recovery on ventilation in order to meet the step code targets. Okay, so let's switch gears a bit here. We're going to talk a little bit about indoor air quality. Filters. So this is kind of, I'm not sure how common this is, but it's certainly something that could be done, and I'm sure there's the possibility with products on the market today. Personally, I haven't come across it yet, but there's been talk about this, or at least this is one idea. You may not necessarily have an air quality issue now, but if you were concerned about it, like let's say you had an intended occupant that could be sensitive to poor outdoor air quality, then you would maybe want to have an allowance to put in a higher performance filter, whether that's a MERV 13 or 14 or higher, whatever, a HEPA filter, activated carbon. Any of these strategies could help improve your air quality inside just by filtering the air from outside. The other thing to think about too is using a dedicated outdoor air system, which is basically just a 100% outside air system rather than a recirculating air system. If you're using a recirculating air system, you may be picking up internal contaminants and reintroducing them into the space. So using just fresh air and then exhaust would be potentially better. Do you have a question? So again, as to the last point, dealing with internal pollutants, use a dedicated outdoor air system. Then you can separate your ventilation from heating and cooling. So this is good for energy performance as well as for not introducing more internal contaminants back into the space. Okay, so we're getting close to the end here. I do have a couple examples, but I'm a little bit ahead of schedule. So just so far, how's everyone doing? Do we have any questions?
So we talk about step one now, is required HRV. Is that what you would require HRV in houses, or is this just talking about
So I would say that yes, a house would require an HRV for a Part 9 step. Part 9. Yeah, I would think so. I don't know off for certain because I don't work in Part 9. But just looking at the targets, I mean, there shouldn't be much. It's the same building physics that's happening. And you essentially need HRVs for pretty much all the step code levels for all buildings. It's just kind of a given. There might be some cases where you may be able to get away with it in like a step 1 targets are kind of different because you're not modeling against a TEDI target. You just have a reference building. And the reference building is frankly really poor. So you can beat it pretty easily, and you can definitely get away without HRVs in that case. So I would think it would be the same for Part 9 homes, but probably not past step 1.
So even the restrictive requirements from 1956 may give you, like, if it was, they'll probably make you do step 1 without having HRV, right?
Potentially. Yeah, I don't know for sure. Not familiar.
HRV is not mandatory thing for step 4. It's actually the targets which are set to make you have HRV.
That's right.
What you do.
Yeah, exactly. Yeah, and that's the whole beauty about the step code is that it's not telling you what you have to do. It's just telling you where you need to get to. So you can decide how you get there, but what we know is that we're setting aggressive targets for a low heating load. And if you look at your heating demand in a building, without an HRV, the ventilation is very high. And it's a very easy technology. It's very effective. It's low cost. It's reliable. So it's just plan for it, basically. Yes?
On screen, referred to ERV.
Ah, yes. Good call.
I've seen ERVs requested more frequently.
Okay.
What is the difference?
So an energy recovery ventilator versus a heat recovery ventilator. So the energy recovery ventilator is also going to transfer moisture. The heat recovery ventilator only transfers sensible heat. So basically there would be, let's say, an aluminum heat exchanger. So it's air sealed, there's no vapor permeability whatsoever. You have warm air going out, you have cold air coming in. The cold outside air is going to get warmed up by the outside air, but any moisture in that exhaust air is going to stay in that exhaust stream. Whereas an ERV, you could have some transfer of moisture in your warm, moist exhaust air transferring over to your dry, cold outdoor air coming inside of the building. It turns out that it's really not significant here in this climate. If you're in northern BC or in the interior of BC, it could be more important. But since buildings in BC in general hospitals would be an exception, don't typically have humidity control, then you're not really trying to keep that moisture inside the building.
All HRVs and things like ERVs have a compensate level.
Mhm.
HRVs often don't require it, and often there's not much moisture put on. In an ERV, is it more likely to
I would think-
moisture more frequently?
I think it would be the opposite. So the ERV would allow the moisture a path to transfer from the exhaust into the fresh air. So there would be less that would be. It has another. Yeah, it has another way to get back into the building. So it would be potentially useful for comfort. So if you lived in a northern climate, like I grew up in Smithers, it's pretty cold up there in the winter sometimes. And yeah, the air by nature can only hold so much moisture when it's that cold. So even if it's 100% humidity, it's very dry. And so in your house, let's say you're cooking and people are breathing and there's some moisture in there, it's definitely more comfortable. People, like a little bit more humidity in the air. So if you had an ERV, you would have some of that moisture come back into your building. And that's really all it is. It's not really a significant factor for buildings in BC. It can become an issue for the opposite reason, to keep moisture out of your building in humid climates like Toronto. So in that case, you could have lower humidity inside, and then you would have actually like active mechanical cooling to dehumidify the inside of the building, which is costing a lot of energy. If you have an ERV, then that can strip the moisture from the moist air coming in and put it into the drier exhaust air going out. And so it kind of can work in reverse. So those are the applications I've seen those used in mostly, and I don't think there's a significant difference between them in our climate.
Do HRVs come with some kind of a panel where people can control the temperature below which the HRV will recover the heat, or is it automatic, or how does it work?
So that would be It wouldn't be like a panel that they access. It would be set up in the controls for the HRV. So first of all, you'd have to have a bypass, right? And then it would be a matter of controlling when does it go into bypass mode versus non-bypass. I'm sure for most of the smaller HRVs with a bypass, it would be a simple bypass or not. If you get into larger systems for commercial buildings where you have like a heat wheel, an enthalpy wheel, so you have a wheel that's rotating and it has a medium in it and often has desiccant for enthalpy, for moisture exchange. It's rotating through the warm exhaust air, slowly getting heated up. It has some mass to it. And then when it comes into the outside air side, it's warm and it's losing its heat to that cold air coming in, and it's preheating that air coming in. You can vary the speed of the wheel, where if you have it stopped, it's not doing anything. If you have it going at an optimal speed, it's recovering heat, so you can modulate the heat recovery. And that would be done in like a building automation system.
But for those without the bypass, is it recovering heat during the summer months?
All the time.
Like it seems like pointless for a system to be recovering heat during the peak summer.
Yeah, and that's exactly why it could be useful to have a bypass. However, it's not that big of a deal. We've actually modeled it with and without just to see like how much of a difference does the bypass actually make. First of all, the ventilation rate is quite low for a residential suite. So you're providing air, sure, it's going to be a little bit warmer than it was otherwise. But let's say it's 25 degrees in your suite and it's 22 degrees or 20 degrees outside. Let's say it's 20 degrees outside and 25 inside, right? And if you have 100% heat recovery, it's going to be coming in at 25 instead of 20. At a fairly low flow rate, that's not going to be a huge difference, particularly if you have an open window. If you have an open window, that's a very small deal in the grand scheme of things. It can have an effect for sure, and we definitely want to see bypasses on like larger systems. Like if you're using a central heat recovery ventilation for a building, then absolutely have a bypass on that. But for a smaller system where you're having a hard time fitting it in the ceiling and everything, it's not probably very common to do that.
So in a way, when you have HRV systems installed and the way you say it runs 12 months, 24/7, then in summer, you can open the windows or you still have closed windows and the HRV takes care of the ventilation. How does it work?
Yeah, the HRV would typically be running all the time, regardless of if you have your window open or not.
Okay.
Yeah.
You can open the windows and have that comfortable
Yeah.
temperature.
You'll just have a little bit more fresh air. I mean, like in a more complicated thing, you could conceivably have a contact switch on your window. This is something that could be done in like a commercial building, where if you open that window, the system knows that the window is open and it turns the ventilation off, saying, okay, you got your window open, you're already getting your fresh air. But that would not be something you would see in a residential building. For the bathroom? Yeah, so the bathroom exhaust goes through the HRV. Yeah, good point. So you would need the HRV to run because you need to be exhausting your bathroom per building code. Good point, Wilma. Okay, so a couple of quick examples here. So yeah, we're just getting towards the end here. So here's a project. I didn't have time to pull the graphics for it, but I think it was a useful example. So there's a small affordable housing project. There's no mechanical cooling in the design. But then we were told that, and it's actually, this is on Elmbridge because it's on Elmbridge Way. It's very close to here. And so we said, great, the climate looks fine. We can use operable windows and we're achieving just totally acceptable comfort. It's great. And it's even shaded by some tall buildings nearby. And there's some trees. So that was fine. But then it has another consideration that prevents people from using windows as an acceptable method of cooling them or maintaining their comfort, namely the aircraft traffic, the noise from it. So City of Richmond actually has a bylaw that says, no. If you're this close to the airport, you need to have your building, show that your building is going to be comfortable and comply with ASHRAE 55. So this is no longer the overheating limits without opening your windows. And so that resulted in us saying, well, We looked at some options to see if we could put a cooling coil and HRVs, make the HRVs bigger, do these different things. We even looked at possibly saying, well, what if the people could open their windows during the day and then they close it when they had to sleep? Because if it's only an issue for them having the noise when they had to sleep, then maybe we can model it with windows opening during the day, which is probably splitting hairs, but we ended up just putting cooling in the building and because of the noise issue. So another example here. So this was a project that's using a Pitt Meadows climate file. So I forgot to point out, or meant to point out earlier. So we did some research for BC Housing on future climate and the risks of it, which is sort of a precursor to the work we did for this this design guideline. And it was on a particular project, and we went pretty deep on some of the risks for different climate scenarios. And I believe, and Wilma, correct me if I'm wrong, that there's a new requirement in the BC Housing Guidelines for 2019, their design standards, now requires 20 hours of overheating. That's the limit for all projects, not just for vulnerable occupants, but for everyone. And my understanding is that this is basically saying that, well, we know that the climate is warmer now than it was for the files that we're using, and that it's only getting warmer. So if we use a 20-hour limit for now, that'll be sort of equivalent to a 200-hour limit in the future, something like that.
It's especially because the 200 hours is a rule of thumb.
Ah.
Just want to set a ceiling. The studio thing, we started with it.
Right.
Don't know, just want to set a ceiling. We don't know what it means, 200 hours. So that people won't go.
Yeah.
Too long. But actually, almost in every housing project, whether it's social housing or not, you have vulnerable populations. You have your grandma at home. You have people who could be pregnant. You have little young infants who have very little ability to regulate their temperature. So we actually think 20 hours is more appropriate. The other piece is in Toronto Public Health has done a research and on this subject, and they've set the temperature at 26 degrees Celsius, beyond which is illegal to rent a space out.
Oh, wow.
Yeah. So we in the guideline, we've also included, we recommend people to check that the temperature doesn't go beyond 26.
Right. Yes, I have. Yeah, I saw that. So for this particular project, we were looking at it, trying to get the project under 20 hours. And the thing is if you look at, I can't remember, I don't know if I did it for Pitt Meadows, but if you look at the City of Vancouver's climate file, just with the peaks that it has, inevitably, even if you were in an open air gazebo, like you're outside, there's no internal gains, there's no solar gains, just the temperatures with the spikes that occur in that climate file, I think you end up at 11 overheating hours. So that's before you even have that's if you had the perfect natural ventilation and no solar gains, no internal gains. So trying to hit 20 is very challenging. Maybe a little bit different for different climates, because of course the targets will change, but it's a very tight target. And so what we're seeing is that it's pushing things to at least a partial cooling solution, if not full cooling. So for this one, we had a bit of a challenge with the orientation. I mean, I think this is pretty much our worst case scenario. The west face of the building being the long end of the building being facing west. So we looked at some different options. So we have central ventilation, and we looked at with a cooling coil in the central ventilation, just using basic ventilation rates, not using increased rates. And it wasn't bad. We had, up here we had 66 hours. It's not down to 20, but it's pretty good. So we felt good about that, especially because it has that exposed west face. Just to double check the impacts of the cooling coil was having, we turned it off and ran it again, and we ended up with 235. And again, this is also in conjunction with having people opening their windows. So they're receiving a little bit of cool air, but they're also able to open up their windows. So then looking at the orientation, I rotated the building so that the long axis was east-west, and this is where we achieved 17 hours. So yeah, we made it under the 20 with a partial cooling solution. So we're pretty happy with that. This project is still under design, so we may end up doing some other shading strategy rather than rotating the building. It may not be possible on the site, but at least we were showing that if we control the solar gains appropriately and add that cooling, it is feasible to get underneath the 20 hours. And then as a final run, just to sort of double check, and this goes back to the insulation, I increased the insulation value of the wall just as a test. Is that going to impact it? Because we were using a similar model, not this model, and this model is going to have a much better envelope, which we hadn't detailed out yet. So turns out in this case, it wasn't actually worse. It was actually slightly better for overheating with a more insulated building. But again, this is with our optimistic, it's sort of an optimal control strategy on the operable windows, that they're being opened and closed exactly when they need to be, which is not necessarily realistic. It's feasible, but not realistic. So just before we finish up here, just to recap, hope you guys have at least picked up some of these things, understanding a little bit about how the step code looks at overheating, in terms of it being these upper limits, that's not ASHRAE 55. How this is different from previous code. I mean, I don't think as far as I know, we didn't have a overheating limit of any sort. Maybe some local jurisdictions like Richmond had ASHRAE 55 requirements or something like that, but otherwise, I don't think there's anything there. There should be some sort of summary of overheating limits and the overheating limit values, where they came from, how they were determined, and maybe some of the modeling that was done to determine the outputs from the model, particularly for any natural ventilation. And then, of course, I hope you have a little bit more of an insight into what the challenges are as the weather, the climate changes, and as we get buildings pushed to a higher level of performance. And so, just a reminder that the full guideline with much more detail about this topic is available on the BC Housing's website. And that's time for some questions. We answered them all along the way. Yeah.
On the line, does it have like a sample report that was we're seeing like what the issue
I believe that we're working on one. Yeah. That's good. That's good to hear, though, because it means, it's going to be something that people are interested. Yeah, exactly. Yeah. So because there's some methodology about it too. It's like, how do you do it? How do you evaluate it properly? I mean, we've spent some time looking into it, and there's been other people working on it as well. So we're going to pool those resources and make sure people have a bit of a guideline as to, okay, how do you go about evaluating this, and what are the outputs that you're looking for?
Just wanted to let you know, actually, Fuku Engineering had given a report on BC Housing project. This is, we are using as a template to develop a report format that can be used by others. So we already have gone through that process. So we are now preparing something to share.
Is the BC Housing project designer who's responsible for employing an energy modeler to specify the heating, air conditioning, air modifying system? So you would be employed as a contractor to design the...
We would be we'd be assisting with the design of the system. So we operate as we're kind of a little bit different than a lot of the energy modeling that's out there. Often you'll see energy modelers working as part of another design service, so like usually with mechanical engineer most commonly, which I've worked in a mechanical firm doing modeling, or with architectural sometimes. And sometimes also with building envelope firms. The thing is like energy modeling is touching on, architectural stuff, building envelope, mechanical, all sorts of things. We are just energy modeling, building performance consultants. So we will consult and we will work with the designers to help them design a building to meet targets. It's fun. It's tedious, but fun. Any other questions on this hot topic? Pun intended. Thanks, Wilma. Yeah, it's warming up, definitely. Okay, all right, well, thank you, everyone.